All right, you are most likely here because you're about to take the types of waves quiz. So I think a good place to start would be for me to give you a definition of a wave. And there's my definition. A wave is a disturbance that moves energy. So you might be thinking right off the bat that, well, hold on, if you've got a hallway and you roll a bowling ball down the hallway, it is certainly moving energy. But the bowling ball is an actual thing. It's not a disturbance. I'm talking about an energy-carrying disturbance that goes from one place to another, like this. Think about a water wave. Let's say you've got a big lake and the wind is blowing and it develops some big waves. If the wind stops blowing, what does the lake do or the ocean do? It just goes right back to zero where it was before the disturbance was there. So that's what I mean by a wave. Now, if you want to, it's probably worth my time here. Every year, a student or two will say, but Mr. Mock, what about a surfer? A surfer is on their surfboard and they're moving from one place to another, but they're moving on the disturbance. They are not the disturbance. They're moving on the disturbance. The surfer is actually just taking advantage of this hill shape here and using gravity to ride the wave. So there's my definition of a wave. It's a disturbance that moves energy. So is a wave a one-time thing, or is it repeated over and over like my drawing here? Well, it can also be a one-time thing. Like if somebody blows up a firecracker or something, there's a little explosion. What happens is there's this sound wave that travels outward in all directions, and that's a one-time thing. So that's also a wave, because once the sound wave travels by, the air particles are right back where they were before they started. So waves can be a one-time thing, or they can be repetitive. So to answer the question, does the medium move? Well, we have to know what a medium is first. So there's two categories of waves here. I've got waves that need a medium and waves that don't need a medium. So what is a medium? Let me give you a definition. A medium is what the waves go through. So right now you're listening to me because sound waves are traveling through the air. So the air is the medium. Or an earthquake happens somewhere. You can't have an earthquake unless you have earth for the wave to go through. So a medium is what the waves go through. Or if you've ever gone underwater and clanked two rocks together, you know that sound can go through water. It can go through liquids and solids too. So a medium is what the wave goes through. So going back to my question here, does the medium move? Well, yes, it does while the wave is going through, while the disturbance is there, yes. But once the wave is past, then I'm going to say overall, no. Once the wave is past, the medium goes right back to where it was. So if you've got a speaker making some sound, it's pulsing these air particles all over the place. As soon as you turn the speaker off, the air particles go spread back out the way that they were before the sound was there. So underneath of waves that need a medium, I made two categories. One category says transverse, and the other one says compressional or longitudinal. So let's talk about transverse waves. A transverse wave, let's think about this example. Let's say a person ties a string or a rope to a tree somewhere, and the person waves their hand up and down. When they wave their hand up and down, they create a wave that goes left and right. They make this pulse that travels left and right. So these two things are perpendicular to each other. So the energy the person adds is going up and down, but the wave is going left and right. So I'm going to write this. I'm going to write the energy is perpendicular to the medium motion. And contrast that with a compressional wave. Let's say we've got a ceiling. Somebody hangs a slinky from the ceiling, and they reach up and they pull the slinky down. So they're adding energy up and down. And when they let the slinky go, what does it do? It boings back and forth, up and down. So in this case, they are parallel. The person added the energy up and down, and the slinky boinged up and down. So in a compressional or a longitudinal wave, the energy is parallel to the motion of the medium. So let's talk about this. I said this was a rope. This was a slinky. Another example of a compressional wave is sound. So there's animations all over the internet. This one comes from a professor named Dan Russell. This animation here, this is a transverse wave. A pulse goes up and down, and this ripple here goes toward the right. And this one is like a speaker, like an audio speaker, like a car speaker. This red surface is the speaker's panel, and it pulses out and it hits the air particles, and you can see this disturbance traveling through the air. That is a sound wave or a compressional wave. This little mushed up part of particles, bunch of particles that you see moving, that's called a compression. In the past couple of years here, I see that he's updated this animation, and here is like a speaker making lots of pulses. So we're supposed to imagine a speaker on the left here. You can see these compressions look like they're going across the page because they are, but if you pick out any one particle, that one particle, all it's doing is moving back and forth a little bit in place. So these bunched up particles here, those are called compressions, and in between, those are called rarefactions. That's because, think of it like this, it's rare to find air in between the compressions. That sounds kind of strange, I know. So here's a speaker that I drew, and that speaker is pulsing out left and right, and as it does so, it makes these compressed areas of particles. We call those compressions, and where there's fewer particles in between the compressions, we call that a rarefaction. So I'm closing in on 7 minutes. I knew this was going to be a longer video, but I'm going to try and finish up. Let's go over to the right and let's talk about waves that don't need a medium. These waves are special. What the heck can that, how can you have a wave that doesn't go through anything? Doesn't every wave have to go through something? Well, no. These waves are called electromagnetic waves, and they can go through a vacuum. So what is a vacuum? A vacuum is just a place with no matter. So an X-ray, if you have an X-ray and it's traveling through space, it's just going to go through space forever because it doesn't have to have anything to go through. It doesn't need a medium. And the same thing is true for all these waves. And we call them electromagnetic. They are all transverse, and the long ones are radio, the shortest ones are gamma, and there's all these different lengths of waves in between. And the ones that we humans can see are called visible. So when you look up in the sky at night and see a star, that's because visible waves have traveled through the vacuum of space to get to your eye. But the topic of the electromagnetic waves is probably best left for another video because I'm just about to hit 8 minutes.